Hi everyone, I'm Dorsa Sadigh and I'm a graduate student working with Sanjit Seshia and Shankar Sastry. And today I want to talk about correctness and control for human cyber-physical systems. So this talk built up really well on the previous talk and also Aaron's talk. But what I want to focus on mostly is correctness and control for these systems, for these human-in-the-loop systems. So we have already seen robotic surgery. That's a good example of human-in-the-loop systems. Other examples are semi-autonomous driving, flying, so switching from autopilot to actual flying, and controlling drones from the ground. So these are all examples of human cyber-physical systems that we already interact with in our everyday lives. But one common thing between these four examples is they're all safety critical. So we are putting our lives in the hands of these systems. And what we really care about is being able to give guarantees about correctness of these systems. And if they're going to fail, can we figure out why they're going to fail? And can we kind of go to a safe mode in such scenarios? So let's look at it from a more abstract view. So we have an environment that's going to be a green box around us, and we have a robot and human interacting with each other, and there's an interface layer in between. So there's a whole area of research on just that interface layer. In addition to that, we have a setting that tells us if you're using a shared control or a switch control setting. So we get a human's control, autonomous control, and we either add them together or switch between them. And at the end, what you want to do is you want to perform a task. You want to do robotic surgery. You want to drive a car. So we have the human, system, and environment combined together, satisfying some specification, some objective that you want to do. So there are a lot of problems in this box, like a lot of problems on each side of them. But one specific problem we want to handle and we want to look at is the challenge of detecting when the robot is going to fail and switching to the human afterwards, and for the human to take control and figure out the failure. So we want to figure out why and when the robot fails and transfer to the human in such scenarios. All right, so let's look at a concrete example. So let's look at driving. And let's say that you want to make an unprotected left turn. So what we do is the red car is ours. We go in the middle of the intersection on a green light, and we want to do an unprotected left turn. So how do we do it? We just wait there until all the cars leave. And then after that, if it is safe, we make the left turn. And a lot of times, you're just in the middle of the street on the red light, and we can't do it. Or we change our objectives. Like, we might just go straight. Like, if I'm on Shattuck and University, I just drive up University. I decide I can't do it. Let's get on Oxford or something. Or make a right turn instead. So humans are really good at deciding what to violate. They're violating something. We can't give this to a Google car. Google car cannot decide how to figure out the situation. But humans are really good at deciding what to violate and bend the rules. So these are the situations you want to transfer to the human beforehand. And if you want to transfer to the human, you want to satisfy some sort of criteria. We can't just transfer to the human immediately. So we want to satisfy these criteria, things like monitoring for failures, detecting when failures are going to happen. We want to be minimally intervening, meaning that we don't want to intervene too much. We want to just intervene whenever it's necessary. We want to give sufficient time to the human. I can't just tell the human, oh, you're going to die in 1 second. We have to give them enough time to figure out how to solve the problem. And we also want the autonomous part to be provably correct. We don't care about the human. Human can do whatever he wants, but we want to make sure the autonomous part, we have guarantees for that. It's going to be safe. So these are our criteria, and I don't have time to get into details of our technique, but the overall idea is we are looking at this as a two-player game between environment and system. And what we do is we extract all the possible ways of environment winning, which means all the possible ways that we are going to find a failure. And we can represent that in a counter strategy graph. That's the graph below. And what you want to do, all we want to do is we want to find a cut of this counter strategy graph. So this cut is going to allow us to find these environment assumptions, things that we need to look at the environment, and in addition to satisfying the criteria. So the details of that are published in TACIS 2014, or you can talk to me at the DOP Center during the poster session. All right, so far I talked to the case that, well, if the robot fails, you want to transfer to the human. Naturally, there's the other case too. What if the human fails? If the human fails, we also want to transfer to the robot. So we want to have a smooth transition between the two. So what we did in this work was we basically tried a data-driven and also model-based approach to do human modeling and to verify our human models. So we used a car simulator, and we tried to gather data from the car simulator. These are trajectories from the car simulator representing the environment and human state. So if human is attentive or distracted, if you're holding a phone or not. All of these are represented in the trajectories. And then on one level higher, we modeled as a Markov decision process. And then what we did was we used some of the formal methods ideas, and we used model checking to use this model of Markov decision process and our property. It could be a safety property, some verification property, running out of the lane, and see if our model satisfies the specification or not. So this way we have quantitative reasoning of when the human fails, or how much the human fails. in driving. So yeah, the results of that are also at AAAI 2013. All right, so for future directions, what you want to do is you want to look at more expressive human models and look at other types of behaviors, risks, and perceptions in the humans. From the control side, you want to look at other types of controllers, like MPC. Like in this work, we looked at reactive synthesis. You want to look at all these other types of controllers and detect failures in such scenarios. And also, you assume perfect information in our models. You want to look at uncertainty when we have uncertainty in the models and all that. Yeah, thank you.